All right, guys, so today's warm-up questions, the first one says, if the frequency of a wave quadruples, what happens to its wavelength? And although we haven't yet talked about light, we have talked about waves, and we have an equation that we're able to use that relates frequency and wavelength to each other. It's the first equation at the top of my board over there that says that the velocity of a wave is equal to its wavelength times its frequency. And the relationship described there is the same as it's going to be for light as it was for mechanical waves. So if you take a look at that formula and you were to quadruple the frequency, keeping the velocity the same, then yes, that's exactly what we do. So Tierra said 1/4. It would, they're going to be inversely proportional to each other. Wavelength and frequency have an inverse relationship, and so if you quadruple the frequency, your wavelength will be 1/4 as much. That's your answer to number 1 for the warm-up. Number 2, when it storms outside, which do you observe first? A flash of lightning or a boom of thunder? And I heard it. Lightning. Anybody know why?
That song by Imagine Dragons.
Not because of the song by Imagine Dragons, but I think Drew said it.
It says lightning.
Yeah. The speed of light. The speed of light is faster than the speed of sound. Now they're both faster than we can drive or run, obviously. But light is quite significantly faster than sound, and that's going to be the focus of our notes today. So we're going to get more information on light, how fast it travels, some different forms of light, and even use that same formula that we just looked at in the warm-up. Okay, your homework assignment, which you will be starting at the end of the period, is 1401.1, electromagnetic spectrum problem set, and then you do have a unit summary this unit as well. All right, guys, let's go ahead and get to the notes. Some of this is going to sound really familiar because we have just talked about waves in our last unit. So we're talking about waves again, but now we're going to be talking about another type of wave. Because, first of all, they both have kind of a similar definition. A wave is a disturbance or oscillation that travels through space-time accompanied by a transfer of energy. There are two types of waves. Last unit we focused on mechanical waves, which were going to be waves that traveled through a physical medium, and that medium could have been air because sound was an example. We used a string in the lab. We talked about water waves, so all these different forms or types of waves that were in a medium. This unit we're going to focus on the other type of wave that I have up there, number 2, electromagnetic waves. Okay, so the terms that we've already learned for waves in the last unit are still going to apply here. Frequency is still the number of wave cycles that pass a fixed point in a unit of time, so it's cycles per second or hertz. That's the measurement that you'll use. Wavelength is still the length of the wave, the distance from one point through one complete wave cycle to an identical point of the wave. That's still going to be how long the wave is, and it's going to be measured with some distance unit. So meters is our standard unit, but if you have a really small wave, you might see nanometers or centimeters or something else. Velocity, again, is still distance traveled by a specific point on a wave in a specific amount of time. For all electromagnetic waves, this speed is the same. This was not the case for mechanical waves. Mechanical waves, the speed of the wave depended on the medium through which it was traveling. And so sound waves had a certain speed at some temperatures and a different speed at other temperatures. Or a string traveled at one speed, or a wave traveled through a string at one speed, and then you tighten the string and it traveled at a different speed. Okay, and so it depended on the medium. But the thing is, electromagnetic waves don't require a medium. They don't cause oscillation of a medium or anything like that. And so their speed is a constant value. And that value is on my screen right now. It says c, that's what we use for the speed of light, constant c, equals 3.0 times 10 to the 8th meters per second. Okay, so that is going to be the velocity or the speed of light. And that's what we're going to use for all of our light waves. Our equation's the same. Okay, the equation that's up on my board, velocity equals wavelength times frequency, it's the same thing, except that now instead of velocity being a variable, it's always the same number. So we're going to rewrite that equation as c equals f times lambda. That's our constant velocity, speed of light, equals frequency times wavelength. Okay, so it's still velocity, it's just now it's the same velocity every single time. All right, so a lot of this should look familiar. The only new thing up here is this speed of light constant. Okay, now mechanical waves, which included water waves, sound waves, waves in ropes or strings or springs, they all required a medium to travel through. So we had waves in air, and water, and glass, and rock. We're talking about earthquakes. So we had a medium. Electromagnetic waves do not require a medium and are able to propagate in a vacuum, which means they can travel from the sun to the earth through the empty void of space. Okay, sound can't do that, but light can. Both of these, by the way, transfer energy. Mechanical waves and electromagnetic waves transfer energy, not matter. Okay, so you've seen this slide before. I used it in our notes in the last unit because we were trying to compare and contrast electromagnetic waves with mechanical waves. And we still need to be able to do that. So electromagnetic waves are transverse waves characterized by oscillating magnetic and electric fields. And that's what this animation is showing, are these oscillations of electric and magnetic fields. My electric field's oscillating in blue. My magnetic field is oscillating in red. These types of waves do not require a physical medium and can propagate through space because they're not actually causing collisions of matter. It's not atoms running into each other, that domino effect we talked about. Okay, you don't need a medium. Instead, it's just fields. Okay, and so that can exist whether or not you have a medium. All of these waves will travel at the speed of light, which is a constant 3.0 times 10 to the 8th meters per second, or if you wanted to use a different unit, 6.71 times 10 to the 8th miles per hour. Unlike mechanical waves, the energy of electromagnetic waves is determined by frequency, not amplitude. So that's one big difference, because in the last unit we talked about how if the wave had greater amplitude, it had more energy, and we had that equation up there, or that relationship up there, that the energy is proportional to amplitude squared. That is still true for mechanical waves. That is not true for light. Okay, the energy of our light waves, or our electromagnetic waves, is determined by frequency, not amplitude. Okay, so let's go ahead and fill out a table to compare and contrast our sound waves with our light waves. Okay, we know that sound is a mechanical wave. Specifically, though, it's a longitudinal wave. Light, on the other hand, is electromagnetic and transverse. Okay, regarding the medium, sound can travel through any medium. It requires a medium, but it can travel through solids, liquids, or gases, but you have to have a medium. Light, on the other hand, does not require a medium. It can travel through space. It can also travel through air. Okay, and different types of electromagnetic radiation can travel through more dense substances, liquid and solids. Okay, now visible light can't always do that. It could if it's just glass. Solid glass can travel through, but your table that you're writing on, your light waves aren't going to travel through that, at least not visible light. But there are other forms of electromagnetic radiation that could, and we're going to talk about some of the different forms on the spectrum later on in our notes. The frequency of sound tells you its pitch. If you had a high frequency, you had a high pitch. If you had a low frequency, you had a low pitch. The frequency of light tells you its energy, and if it's visible light, it also tells you its color. Okay, so if you have a high frequency visible light, then it's going to be closer to the purple end of the rainbow, that spectrum of color. If you have a low frequency of visible light, it would be closer to the red end of the rainbow. Okay, and we're going to look at that in a minute. But it always describes energy, even if it's not visible. The higher the frequency, the higher the energy, and vice versa. They're directly proportional to each other. Amplitude of sound was what determined its energy. Again, we said that the amplitude squared was proportional to energy for our mechanical waves, like sound. That meant louder sounds. Okay, so for sound, amplitude was loudness, or the energy of the wave. For light, amplitude doesn't have anything to do with energy, but it does have to do with the intensity or brightness of the light. So the greater the amplitude, the brighter that light will be. Speed of sound is about 340 meters per second in air. Again, it depends on your altitude, it depends on the temperature. There are different factors that are going to affect that speed because it does depend on the medium. But it's about 340, I think it's actually 343 meters per second at sea level and room temperature. But somewhere in that ballpark, depending on those other factors. Light, on the other hand, travels at a constant 3.0 times 10 to the 8th meters per second in a vacuum. Notice it's significantly faster than sound. They're both fast, but light is significantly faster than sound. Light does travel at different speeds. If you have a different optical density, it can travel through the air, but it is a little bit slower. I will say it still rounds to the same value. It still rounds to 3.0 times 10 to the 8th through air. But if you have something that's even more dense, it may travel a little bit slower. So it depends on what it's propagating through. But this is the speed of light we use for traveling in a vacuum or in air, which is what we are going to deal with most of the time. I don't have this up here, but remember both of these, sound and light, both of these transfer energy. Neither of them transfer matter. They have that in common. Okay, so both of them cause a transfer of energy, not matter. So here is the electromagnetic spectrum, and you're welcome to draw this on your paper or at least list these maybe in order. But you have radio waves all the way over here to the left-hand side, and as we read it to the right, it's radio waves, then microwaves, then infrared, then here's our visible light spectrum, our rainbow, then ultraviolet, X-rays, and gamma rays. Okay, so you need to have some kind of idea about what falls into this spectrum or to be able to compare, let's say microwaves to X-rays. If you take a look, we're going to fill in some blanks down here to describe what's happening to the wavelength as we read across this image from left to right, what happens to the frequency, what happens to the energy. So looking at wavelength first, and there's even a wave drawn up here to kind of illustrate this. The wavelength of radio waves, for example, as you're to the left side of the image, these are very long waves. And as you move this way, they get shorter and shorter. So your wavelength goes from long to short as you go across this image, the way that it's drawn. Okay, now if you find a spectrum that lists them flipped, then obviously you need to pay attention to that. Okay, but your longest wavelength up here is radio waves, your shortest is gamma rays. Frequency. We already know that frequency and wavelength have an inversely proportional relationship. So if I have a large wavelength, I need to have a small frequency. There are fewer of these waves per second because they're so long. Okay, and so my frequency here is going to be low. Over here it's going to be high. So low frequency radio waves, high frequency gamma rays, and of course everything else is in between. Energy is directly proportional to frequency. We just mentioned that in the notes a second ago. So where the frequency is low, the energy will also be low. Where the frequency is high, the energy will also be high. Okay, so looking at this, that means that the wave over here all the way to the left-hand side, our radio waves, have very low energy, whereas our gamma rays have very high energy. Okay, and so you can get an idea of some of the properties of these waves. And I'm going to ask you some questions in a second. So let me go ahead and go to the next slide because I have them here. Okay, so looking at this, which electromagnetic radiation has the lowest frequency? Hopefully you wrote it down a second ago. Which one has the lowest frequency? You should have written it down a second ago. It was just on the screen. Okay, yeah, so you have your radio waves are low frequency. Which ones are most dangerous to humans? Gamma. Okay, I'm going to go back to this real quick. These high energy over here, and you can tell, radio waves, microwaves, infrared, visible light, these are not dangerous to us. Okay, we're not afraid of being underneath these lights. We're not afraid, hopefully, of standing in front of your microwave. If you are afraid, you shouldn't be. Okay, I know there's a lot of weird stuff out there. Radio waves are all around us right now. Okay, those are not dangerous to us. However, you are well aware that ultraviolet light is dangerous. That's why you put on sunscreen. Okay, you put on sunscreen to protect you from that high energy ultraviolet radiation because you'll get sunburn from it. You could get skin cancer from it. Okay, same thing, and actually more so with x-rays. If you've ever had an x-ray, that x-ray technician puts a lead vest on the part of your body that's not being x-rayed. Like if you went to the dentist, they'll put a lead vest on you and they leave the room because they can't be around x-rays every single day. Okay, you can't have too many x-rays because it can damage your cells and it can cause cancer because they're high energy. And they penetrate not just through your top layer of skin, like your ultraviolet, it's just your skin, okay, but they can penetrate further, which we know because we use them for that medically. Okay, gamma radiation, this is the most dangerous one to humans. Okay, and gamma radiation is what people have like whenever there is, like if they get radiation poisoning, like in Fukushima, whenever there was the nuclear power plant that went down and there was stuff leaking, and you know, they're worried about the whole thing just exploding. You have gamma radiation with that nuclear waste, and that's really dangerous to be around. So that's why they bury this stuff in like the nuclear waste, not the waste, but they bury the waste in like lead, cement, lead encased like blocks in the desert where nobody lives, because they're trying to limit exposure to people, primarily, but hopefully some wildlife. I mean, I know there's stuff out there. But that's why they do that, because this is the most dangerous by far. Okay, so as you read across the spectrum from left to right, they get increasingly dangerous to humans. Which one travels the fastest? Which one do you think is the fastest? Yeah, they're all the same. Okay, don't fall for that question. Okay, they are all the same speed. Guys, they're all light. Okay, they all travel at the speed of light. I know they don't all say light up there, but they all travel at the speed of light, 3 times 10 to the 8th meters per second. So again, be able to answer questions like this about the electromagnetic spectrum. Okay, now visible light is the only part of the spectrum that we can see. But there are other organisms that can see outside of the visible light spectrum. Okay, there are bees and bugs, certain types of insects that are able to see ultraviolet light. Okay, so they're able to see part of the spectrum we can't. That's why they're attracted to like white flowers or those bug zapping lamps. Okay, other animals like certain species of snakes and mosquitoes can actually see or sense infrared radiation, which would make sense because that's basically heat vision. Okay, it would help them to, you know, for snakes to find prey or for mosquitoes to find you in order to, you know, survive. So there are organisms that can see outside of this range, but for humans, we can see from about 380 nanometers to about 750 nanometers, and then everything else is outside of our visible range of spectrum. So again, there are some animals that can see here in this infrared and then in the ultraviolet that are just outside of the visible light spectrum. So we have this whole spectrum of light with all of these colors, and I want to talk now about where those colors of light are coming from. And so this is going to be kind of a miniature chemistry lesson. But you should know by now that electrons orbit atomic nuclei in energy levels. So we have our nucleus, and then we have these energy levels around the nucleus where the electrons can be found in their orbitals. When you add energy to a material, okay, whether that is a filament in a light bulb, or with these fluorescent bulbs, a gas inside of a tube, or maybe you did a flame test lab in chemistry, okay, in which case you took some salt and put it in fire. Okay, but whenever you add energy like heat or electricity or whatever, you can cause the electrons in that material to become excited. Okay, and that means that they jump up to higher energy levels. So an electron that would normally be orbiting right next to the nucleus might now be, you know, significantly farther away. When those electrons fall back down to ground state, they have to get rid of the energy that they took in, and they get rid of that energy sometimes it's in the visible light spectrum, but they emit light. And it can be different colors depending on how far the electron's falling, how much energy it has as it falls. So again, these electrons can move from one energy level to another by gaining or losing a distinct amount of energy. And I say distinct energy because it's not like a continuous spectrum of energy. Instead, it's like rungs on a ladder, where they can gain very specific quantized amounts of energy, and they would basically be stepping on one of these rungs of the ladder. Okay, you can't step in between two rungs. So there are very specific amounts. However, the ladder doesn't look like this because our energy levels in an atom are not evenly spaced. Instead, when you're closer to the nucleus, those energy levels are farther apart, and as you get farther away, those energy levels start to get closer and closer together. Okay, and so your ladder would look kind of crazy like this ladder right here. But when an electron absorbs energy in whole photons or quanta, it jumps to a higher energy level. This is called the excited state. The electron will emit energy in whole photons or quanta as it falls to its original energy level. This is called the ground state. So again, this should sound familiar from your chemistry class. Okay, so again, this is how the colors get determined. That's why we're talking about this, because we have all these different colors of light, and we can see these different colors of light because of this behavior of the electrons. Depending on how far they fall, they emit different colors. And so you can see here, if they fall a shorter distance, that's not as much energy loss, and so you're going to have lower energy light. If it's visible, it might be red or orange or yellow, like toward that end. If they fall a greater distance and there's more energy being given off, you're going to have light that's closer to the other end of the visible, other end of the spectrum for visible light, so closer to violet or blue. They can also be outside of the visible range. You can give off other types of radiation. But this is how we know that the amount of radiant energy absorbed or emitted is proportional to frequency. The energy is not related to the amplitude anymore. It's related to the color, okay, of the visible light. So energy is proportional to frequency, and we get all these different colors of light. And this equation right here is what we use to get the relationship between the energy of the light and the frequency of the light. And the equation is E equals H times F, where H is a constant known as Planck's constant, which has a value of 6.626 times 10 to the negative 34th joule seconds. You've seen this equation before. You used it in chemistry. Now, I will say this. We don't actually have to cover this equation. I'm putting it up here to show you the relationship, but we won't use the formula. You do need to know that energy is directly proportional to frequency. But in terms of calculating it, you won't be asked to do that. So you don't have to write down Planck's constant, but you can. It doesn't hurt to have a little bit of extra information. Okay, now when these electrons fall back down, depending on the material that you have, you're going to get different colors. And it gives us what we kind of refer to as an atomic fingerprint, because every single element has a unique emission spectrum. Okay, and here are some of them, examples of 4 of the elements. We have this continuous spectrum. Here's our rainbow. But if you look at the electrons in sodium, those electrons are able to gain, again, very specific amounts of energy, and when they fall back down to ground state, they emit very specific colors of light. And you see these bands that represent the different energy changes that happen whenever these atoms become, or electrons become excited and fall back down. Same thing with hydrogen, calcium, and mercury. But this is known as an emission spectrum, and you can use it to identify an element if you're looking at something and you don't know what it is, or if it's a mixture of things and you're trying to figure out what's in it. This is actually used a lot in astronomy to figure out what the composition of stars are, that obviously you can't test because you can't get to the star and like take a sample. Okay, and so they will use emission spectra to figure out what elements are composed that star. The absorption spectrum is basically the exact opposite. If you take a light source and shine it through a material, that material's electrons might absorb very specific frequencies and energies of that light and leave you with just what's left. Now, the absorption and emission spectra are exactly opposite. So here's hydrogen, for example. You can tell that these are exactly lining up with each other, the colors that are emitted versus the colors that it would absorb. Same thing. So you can use either of them in order to determine the identity of hydrogen in an unknown sample or a mixture of elements, or whatever element you might have. So here's what the question might look like. Okay, you're going to see something like this on your assignment today. I think it's also on your quiz at the end of the unit. So here it says, what element or elements can be found in the star marked unknown? So if you take a look, here's my unknown star. and it has these different bands of light, and you just have to match it up. Like, for example, I know that this sample doesn't have beryllium because this doesn't match up. Okay, these bars don't line up with what's up here. Neither does copper. But if I look at manganese, I can line that one up. I can line that one up. I can line up every single one of those lines on the emission spectra. Therefore, I know that my unknown sample must contain manganese. But it doesn't just have manganese because it has extra lines. So there's something else in there, at least one other thing. I can see, and if I look at strontium, it also looks like it lines up. Okay, and I need to make sure that all of them do, and they will. Okay, and if I do this, I can see I have now accounted for every single one of these lines. So that means that my unknown star contains manganese and strontium. Okay, now if I had more lines, I could see what else is in there, but I'm done. Okay, so that's how the questions might look. Now yours won't be in color, they'll look more like this. Okay, this one says, based on the image above, what elements are present in the mixture? So again, it's the same thing. You have a mixture down here, and you're just going to line it up. I can tell right away element D is going to be in there because it's the only one that lines up with the first line. Okay, so I know it's D. I know it's not G. I can see that that's not there, that's not there. So the question is E in here as well? And again, you can trace those from E to my mixture and see that it contains both of them. Okay, so my mixture here would contain both element D and element E. Questions about emission spectra? Okay. All right, so mathematically, you need to know these relationships. Okay, we talked about the first one in the warm-up. Wavelength and frequency are inversely proportional to one another. You need to know that. It's also described in the equation C equals lambda times F. C is a constant. So if lambda goes up, F has to go down and vice versa. Okay, so you need to know that wavelength and frequency are inversely proportional. You also need to know that frequency and energy are directly proportional as described in the second equation here. Again, H is a constant, so if F goes up, E also has to go up and vice versa. So you need to know these relationships, and of course you should be able to calculate as well. Okay, but you need to know the relationships between some of these variables. So let's take a look at an example calculation. This one says, the blue color of the sky results from the scattering of sunlight by air molecules. The blue light has a frequency of 6.67 times 10 to the 14th hertz. What is the wavelength of this radiation? So I actually took the equation C equals lambda times F, and I divided both sides by F to get this new equation that's already set up for me to solve for wavelength. You can rearrange the equation first, or you can put the numbers in and then rearrange the equation. It doesn't matter to me. But let's go ahead and see if we can solve this. So I have F, I have C, I'm looking for lambda. When I substitute in, I get this. And here's where I want you guys to try this in the calculator. Okay, whenever you're dividing by something with scientific notation, some of you guys are still missing these questions, and we've done it a few times now. You've had to do this in electrostatics. We had a lot of scientific notation. In universal law of gravitation, we had a lot of scientific notation. And some of you, although you knew how to do it, your work looked good, you got it wrong because you couldn't enter it in the calculator. Please type this in the calculator, because if you type it incorrectly, you're going to get the wrong answer. If you type this correctly, 3.0 times 10 to the 8th divided by 6.67 times 10 to the 14th, you should get 4.5 times 10 to the negative 7th meters. Okay, again, double check and make sure you're getting that. If you type them as a fraction like this, if this is what it looks like in your calculator, you should be good. The concern is when you type it in as 3 times 10 caret 8 and then a slash and then 6.67 times caret or 10 caret 14. Okay, when you do that, it will divide only by 6.67 and then it's going to multiply by the rest. So you either need to use the E button instead of times 10 caret, okay, or you need to group this in parentheses, a parenthesis in front of this 6 and after the 14, okay, so that the whole thing stays together. Or type it as a fraction. Okay, so again, this should be 4.5 times 10 to the negative 7th. Are there any questions about the first calculation? Again, you can have some of these written down in your notes for an example. Here's another one. This will be a good one to have as an example. It says, calculate the frequency of a photon of light with a wavelength of 487 nanometers. Again, the question only has to give you one number because another of those values is a constant. So I have a wavelength, 487 nanometers, and I have c. My speed of light is a constant 3.0 times 10 to the 8th meters per second. I'm looking for f. Okay, before I plug everything in, I already know I have a problem. What is my problem? Sorry? Nanometers is my problem. My units don't match. That's my problem. Okay, so I need to make sure to make the units match. I need to convert nanometers to meters because speed of light's in meters per second. I need my wavelength to also be in meters. Now, if you don't know this conversion, you might want to write it down. There are 10 to the 9th nanometers in 1 meter. So if I'm trying to convert nanometers to meters, I need to divide by 10 to the 9th. Okay, if I have meters and I'm trying to convert to nanometers, I'd be multiplying by 10 to the 9th. But there are 10 to the 9th nanometers in 1 meter. Okay, so that means that this is a very small length. 487 nanometers is tiny. And look at this. That makes sense. This is tiny. 4.87 times 10 to the negative 7th meters. That is my wavelength. Now I can solve for frequency. Okay, so c equals lambda times f. There's my speed of light. There's my lambda. I'm looking for f. I'm going to divide both sides by 4.87 times 10 to the 7th. Okay, and that's what goes in my calculator. Okay, so 3 times 10 to the 8th divided by 4.87 times 10 to the negative 7th gives me 6.16 times 10 to the 14th hertz. Again, make sure it makes sense. Okay, and then double check it. Make sure you're typing it in correctly. Questions about this example? All right, I think I've got one more. Let's take a look. Saturn orbits the sun at approximately 1.4 billion kilometers. How long in minutes does it take sunlight to reach Saturn? So I have these pieces of information. I already know that I don't want kilometers, I want meters, so I went ahead and converted that. 1.4 billion kilometers is the same thing as 1.4 times 10 to the 12th meters. Okay, and then I have my speed of light. Now, my equation, speed of light equals frequency times wavelength, isn't helpful here because I don't have a frequency or a wavelength. However, speed is speed. Speed of light is still speed. So it's also equal to distance over time. Okay, and I do have a distance, and I'm looking for a time. So we're going to go back to unit 1, and we're going to use our equation, velocity is distance over time, or speed is distance over time, to solve this one. Here's my speed, 3 times 10 to the 8th equals, here's my distance, 1.4 times 10 to the 12th divided by t. Again, mathematically, I need to get this off of the bottom. I'm going to multiply both sides by t so that I can solve for it. And now I have this. And now I need to isolate that variable by dividing by 3 times 10 to the 8th. So here's how it goes in the calculator. 1.4 times 10 to the 12th divided by 3 times 10 to the 8th, and that gives me a time of 4,666.7 seconds. Again, this is not my answer because the question didn't ask for the time in seconds. I have one more step. The question says how long in minutes. So I know there are 60 seconds in a minute. I can simply divide this number by 60 and I will get 77.8 minutes. So that's how long it takes light to make its way from the sun to Saturn. Anybody know how long it takes to make its way to Earth?
8 minutes.
Approximately, yes.
Even 20 seconds.
Something like that. Okay, so again, I was just curious if anybody knew that. But yeah, much longer time to make it to Saturn. Makes sense, it's much farther away. Okay, so instead of 8 minutes, now we're at 78 minutes, approximately. All right, questions about this calculation? All right, guys, for the rest of the period today, you have an assignment, 1401.1, electromagnetic spectrum problem set. So go ahead and get that opened up and get started. If you have questions, please ask each other or ask me. One little footnote I wanted to include, we haven't done scientific notation in a while, but some of your answers might need to be entered in scientific notation in MyOpenMath, and to do that, you're going to use a capital E the same way that the calculator does it when it spits out an answer. So for example, if you're trying to type this in as an answer, 2.6023 times 10 to the 7th, you can round it to 2 decimal places, 3 sig figs, unless it tells you otherwise, and type it as this, 2.60 capital E 7. It does have to be capital. It is case sensitive. Okay, so again, go ahead and get to work on it. If you run into something where you have a question, please ask. If you don't finish it in class today, it will be homework due by 11:59 p.m. tonight.